You are standing on a sphere of rock, hurtling through an infinite darkness at 67,000 miles per hour. Right now, at this very second, you're travelling faster than the fastest jet ever built, and you cannot feel it. You're also spinning. The ground beneath your feet rotates at over 1,000 miles per hour near the equator, yet your coffee sits perfectly still in its cup. But even these velocities are nothing compared to what comes next. Your planet orbits a star at 67,000 miles per hour. That star orbits a galaxy at 514,000 miles per hour. That galaxy moves through space at 1.3 million miles per hour. And space itself, the fabric of reality, expands in all directions, carrying everything with it at speeds that exceed light itself in the farthest reaches. Every breath you take contains atoms that were once inside stars. Every thought you think is the product of electrochemical signals firing across neurons built from carbon and oxygen and nitrogen, forged in stellar furnaces billions of years ago. You're not separate from the cosmos. You're the cosmos, temporally organized into a pattern capable of contemplating itself. And the scale of what you're part of defies every intuition evolution has given you. The universe extends from the incomprehensibly large to the impossibly small. Between these extremes lies a span of roughly 62 orders of magnitude, 62 factors of 10, a gulf so vast that no human language contains adequate metaphors to describe it. We perceive reality through a narrow window, the slice of existence where our senses function, where our bodies can survive, where the laws of physics permit complexity and consciousness. But this window is tiny. Most of the universe exists at scales we cannot directly perceive, in realms where our intuitions fail and only mathematics can guide us. We are going to journey across the entire scale of existence, from the observable universe at its most incomprehensible vastness, down through galaxies and stars and planets, past humans and cells and molecules, through atoms and subatomic particles, down to the theoretical smallest things that might exist. We will explore not just the numbers, which are themselves staggering, but what these scales mean, how they connect, why the universe organizes itself this way. And then we are going to ask what it means that we sit somewhere in the middle of all this, conscious minds contemplating an enormity that dwarfs comprehension. If you're ready to see reality at every scale it offers, hit that like button and subscribe. Prepare yourselves. We begin at the edge of everything we can possibly know. The observable universe is 93 billion light years in diameter. Let that number settle for a moment before we discuss what it actually means. 93 billion light years. A light year is not a measurement of time, though the name suggests otherwise. It is a distance, specifically the distance that light travels in 1 year of Earth time. Light moves at 186,282 miles every single second. Not per minute, not per hour. Every second, a beam of light crosses a distance equivalent to travelling around Earth's equator more than 7 times. In 1 year, light crosses nearly 6 trillion miles. That is 1 light year. Now multiply that by 93 billion. The mathematics quickly becomes absurd. We're talking about a distance so vast that if you wrote it out in miles, you would need to write the number 5.5 followed by 23 zeros. That is 550 sextillion miles. The word sextillion exists because human language had to invent terms to describe quantities that never appear in everyday experience. Sextillion sits in a family of words, million and billion and trillion and quadrillion and quintillion, each one 1,000 times larger than the last, each one less connected to anything a human mind evolved to understand. To put this in perspective, imagine you could shrink the observable universe down until it fit inside a sphere the size of Earth. On that scale, the Milky Way galaxy, our home galaxy containing hundreds of billions of stars, would be smaller than a single atom. The entire solar system would be invisible, far tinier than anything we could ever hope to see even with our most powerful microscopes. This is not an exaggeration. This is the actual proportional scale. The observable universe is that much larger than anything in our daily experience. But here is the puzzle that has confused many people when they first learn about cosmology. The universe is only 13.8 billion years old. If nothing can travel faster than light, and light has only had 13.8 billion years to travel, then the farthest we should be able to see is 13.8 billion light years in any direction. the observable universe should be 27.6 billion light-years across, not 93 billion. What gives? The answer is expansion, and understanding expansion is crucial to understanding the true scale of the cosmos. The universe is not static. Space itself, the actual fabric of reality, stretches and grows. This is not a metaphor. Space genuinely expands, carrying galaxies along with it like raisins in a rising loaf of bread. When we look at distant galaxies, we are seeing light that was emitted billions of years ago. But in the time it took that light to reach us, the galaxy that emitted it has moved farther away because space itself expanded between us and them. Imagine an ant walking across a rubber sheet toward you. The ant walks at 1 inch per second, a steady pace. Now imagine that while the ant walks, someone stretches the sheet. They pull it in all directions, making it larger. The ant keeps walking at 1 inch per second relative to the sheet beneath its feet, but the distance between you and the ant actually increases because the sheet itself is stretching faster than the ant can walk. The ant makes progress, moving forward with every step, but the destination recedes faster than the ant advances. Light behaves similarly in an expanding universe. Photons emitted 13.8 billion years ago have been travelling toward us ever since, moving through space at the cosmic speed limit, but the space they crossed has expanded behind them, stretched by the ongoing expansion of the universe. The galaxies that emitted those photons are now roughly 46 billion light-years away from us in every direction. That gives us a sphere of observable space 93 billion light-years in diameter. And this sphere grows slightly larger every second as light from more distant regions finally arrives after its long journey. The expansion of space creates another strange effect. Beyond a certain distance, galaxies are receding from us faster than the speed of light. This does not violate relativity because the galaxies themselves are not moving through space faster than light. Space between us and them is expanding, and there is no speed limit on the expansion of space itself. These distant galaxies exist. They contain stars and possibly planets and perhaps even life, but they are causally disconnected from us. Light they emit today will never reach Earth because the expansion of space will carry them beyond our cosmic horizon before their light can traverse the growing gap. And this is only what we can see. The word observable is critical here. The observable universe is not the universe. It is merely the part of the universe from which light has had time to reach us since the Big Bang. Beyond our cosmic horizon lie regions of space that are expanding away from us so quickly that their light will never, ever reach Earth. These regions exist. They're just as real as the space around us. They contain galaxies and stars and perhaps civilizations, but they are forever invisible to us because the expansion of space between us and them exceeds the speed of light itself. The actual universe, the whole universe, could be vastly larger than what we observe. Some theories based on cosmic inflation suggest the entire universe might be at least 1023 times larger than the observable portion, a number so enormous it makes the already incomprehensible size of the observable universe seem tiny by comparison. Other calculations, using different assumptions about the geometry of space, suggest the universe is at least 250 times larger than what we can see. That would mean a diameter of over 23 trillion light-years for the whole cosmos. And then there is the possibility that the universe is infinite. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, indicate that the universe is flat or very nearly flat in its geometry. A flat geometry in the context of general relativity suggests an infinite extent. If the universe is truly infinite, then it contains an infinite number of galaxies, an infinite number of stars, an infinite number of atoms. There is no edge, no center, no boundary. Every point in an infinite universe is equivalent to every other point. You could travel in any direction forever and never reach an end. The observable universe, then, is not a complete picture. It is a bubble, a sphere of visibility centered on Earth, bounded not by walls but by time and light and the relentless expansion of space. Every second that passes, that bubble grows slightly larger as light from more distant regions finally arrives. We see roughly 3 meters farther into space with each passing second, a rate determined by the speed of light. But because the universe itself also expands, regions beyond a certain distance will always remain beyond reach. We live inside a cosmic horizon that we can never cross, surrounded by an immensity that may be infinite, observing only a finite portion of all that exists. To grasp the scale of the observable universe, we cannot simply leap from here to there. The numbers are too large. Our minds, evolved to track predators on African plains and measure distances to trees and estimate the throw of a spear, cannot intuitively process the gulf between 1 meter and 93 billion light years. We need stepping stones. We need to build our way up slowly, scale by scale, each step a new order of magnitude, until we arrive at the edge of everything. And so we begin not with the universe, but with something familiar. We begin with Earth. Our planet measures 7,917 miles in diameter, roughly 12,742 kilometers. If you could somehow walk around the equator without crossing oceans, you would cover about 24,901 miles, a journey of approximately 40,075 kilometers. This is a distance humans can understand because we have built vehicles that travel such routes. Commercial airplanes fly at speeds around 500 miles per hour. At that speed, you could circle the Earth in roughly 50 hours of continuous flight. The fastest jets can exceed 2,000 miles per hour, cutting that time to about 12 hours. We have circumnavigated Earth by ship, by plane, even by balloon. The scale of our planet is large compared to a human, but it is comprehensible. The International Space Station orbits at an altitude of about 250 miles above Earth's surface, moving at 17,500 miles per hour to maintain its orbit. From that height, astronauts can see the curvature of our planet clearly, the thin blue line of atmosphere clinging to the surface, the swirl of clouds, the contrast between ocean and land, the lights of cities glowing on the night side. At this altitude, Earth still dominates the view. The planet fills the window, vast and beautiful and detailed. Continents are recognizable. Weather systems span thousands of miles. The atmosphere appears as a fragile shell, thinner proportionally than the skin on an apple. Now we move outward to the Moon. Our closest celestial neighbour orbits Earth at an average distance of 238,855 miles, roughly 384,400 kilometres. This is about 30 times the diameter of Earth. If you could drive a car to the Moon at highway speeds, say 60 miles per hour, the journey would take roughly 165 days of continuous driving over 5 months. Apollo astronauts made the trip in about 3 days using rockets capable of reaching speeds over 24,000 miles per hour. The Moon is, in cosmic terms, extraordinarily close. It is our nearest celestial companion, tidally locked to Earth by gravitational forces so that it always shows the same face to us. But even this modest distance dwarfs anything humans experience on the ground. The Moon itself is about 2,159 miles in diameter, roughly 1/4 the size of Earth. It has no atmosphere, no liquid water, no protection from solar radiation or micrometeorite impacts. Its surface is covered in regolith, a layer of fine dust and broken rock created by billions of years of bombardment. The far side of the Moon, never visible from Earth, was a mystery until spacecraft photographed it in 1959. Standing on the Moon and looking back at Earth, you would see a beautiful blue and white marble suspended in the blackness of space, the only obviously living world visible in any direction. Push farther out and you encounter the Sun. Our star sits 93 million miles away, a distance astronomers call 1 astronomical unit, abbreviated AU. This distance is fundamental to understanding the solar system and serves as a cosmic measuring stick. Light from the Sun takes 8 minutes and 20 seconds to reach Earth, travelling across the void at 186,282 miles per second. If the Sun suddenly vanished, we would not know for over 8 minutes. The sky would still be bright. The gravitational pull that holds Earth in its orbit would still exist. And then, after 8 minutes and 20 seconds, the light would vanish and Earth would begin drifting off on a tangent, no longer bound to its star. At the speed of a commercial jet, it would take roughly 21 years of continuous flight to reach the Sun. At the speed of light, the journey takes just over 8 minutes. The Sun itself is enormous, 864,000 miles in diameter, over 100 times wider than Earth. You could fit 1.3 million Earths inside the Sun's volume, yet for all its size, the Sun is merely average among stars. It is a G-type main sequence star, classified as a yellow dwarf, neither particularly large nor particularly small, neither exceptionally hot nor unusually cool. It has burned for about 4.6 billion years and will continue burning for another 5 billion before exhausting the hydrogen in its core. The solar system extends far beyond the Sun. Mercury, the closest planet, orbits at 0.39 AU, about 36 million miles from the Sun. Venus orbits at 0.72 AU. Earth, as we know, sits at 1 AU. Mars orbits at 1.52 AU. These 4 planets, the terrestrial or rocky planets, occupy the inner solar system. They are small and dense, made primarily of rock and metal. Beyond Mars lies the asteroid belt, a region of rocky debris orbiting between 2.2 and 3.2 AU from the Sun. The asteroid belt contains millions of objects, ranging from dust grains to dwarf planets like Ceres, which measures about 590 miles in diameter. Contrary to popular depictions in movies, the asteroid belt is mostly empty space. The asteroids are separated by such vast distances that spacecraft can pass through without encountering any obstacles. Jupiter, the first of the gas giants, orbits at 5.2 AU, about 484 million miles from the Sun. Jupiter is enormous, more than 11 times the diameter of Earth and over 300 times its mass. You could fit 1,300 Earths inside Jupiter's volume. Yet despite its size, Jupiter is still tiny compared to the Sun. It would take over 1,000 Jupiters to equal the Sun's mass. Saturn orbits at 9.5 AU, Uranus at 19.2 AU, and Neptune, the farthest official planet, orbits at about 30 AU, nearly 2.8 billion miles from the Sun. Light from the Sun takes over 4 hours to reach Neptune, but the solar system does not end at Neptune. The Kuiper Belt, a region of icy bodies including the dwarf planet Pluto, stretches from 30 to 50 AU. Beyond that lies the scattered disk, and beyond that the Oort cloud, a theoretical shell of comets that may extend 100,000 AU from the Sun, halfway to the nearest star. The Oort cloud is so distant and diffuse that we have never directly observed it. Its existence is inferred from the orbits of long-period comets, icy bodies that occasionally plunge into the inner solar system from unimaginably distant origins. At 100,000 AU, you're about 1.6 light-years from the Sun. This is roughly 1/3 of the distance to the nearest star. The Oort cloud marks the outermost boundary of the Sun's gravitational dominance, the edge of the solar system proper. Beyond this, the gravitational influence of other stars becomes significant. Proxima Centauri, the closest star to our Sun, lies 4.24 light-years away, about 25 trillion miles, or 268,000 AU. If you could travel at the speed of light, you would need over 4 years to reach it. At the speed of Voyager 1, humanity's fastest and most distant spacecraft, which is currently travelling at about 38,000 miles per hour relative to the Sun, the journey would take over 70,000 years. Interstellar space is incomprehensibly vast. Stars are separated by gulfs of empty darkness so large that light itself becomes a slow traveller. Proxima Centauri is a red dwarf, a small cool star much dimmer than our Sun. It is part of a triple star system called Alpha Centauri. The other 2 stars in the system, Alpha Centauri A and Alpha Centauri B, are more similar to our Sun and orbit each other, while Proxima orbits them both at a great distance. In 2016, astronomers discovered a planet orbiting Proxima Centauri, a world they named Proxima Centauri b. This planet is roughly Earth-sized and orbits within the star's habitable zone, the region where temperatures might allow liquid water to exist on the surface. Whether life could exist on such a world remains unknown. Red dwarfs are active stars, prone to powerful flares that could strip away a planet's atmosphere. But the discovery of Proxima Centauri b reminds us that even the nearest stars may host worlds. Our Sun resides in a region of the Milky Way called the Orion Arm or Orion Spur, a minor spiral structure between 2 major arms, the Sagittarius Arm and the Perseus Arm. The Milky Way is a barred spiral galaxy, a rotating disk of stars, gas and dust with a central bar-shaped structure and sweeping spiral arms. The galaxy measures about 100,000 light-years in diameter and perhaps 1,000 to 2,000 light-years thick at the disk, with a central bulge rising to about 10,000 light-years in height. It contains between 200 billion and 400 billion stars, a number so large that if you could count 1 star per second, it would take you over 6,000 years to count them all, working continuously without rest. The Sun orbits the galactic centre at a distance of about 26,000 light-years, travelling at a velocity of roughly 514,000 miles per hour. Even at this enormous speed, the Sun takes 225 to 250 million years to complete one orbit around the galaxy. This period is sometimes called a cosmic year or a galactic year. Dinosaurs roamed Earth the last time the Sun was on the opposite side of the galaxy. The entire history of complex life on Earth has occurred during roughly 2 galactic years. At the centre of the Milky Way, 26,000 light-years from us, lies Sagittarius A, a supermassive black hole with a mass of about 4.1 million times that of the Sun. This black hole, like those at the centres of most large galaxies, does not emit light but warps space and time so severely that nothing, not even light, can escape once it crosses the event horizon. Astronomers have observed stars orbiting Sagittarius A at speeds exceeding 3,000 miles per second, orbits so tight and so fast they provide compelling evidence for the black hole's existence. The Milky Way is not alone. It exists within a structure called the Local Group, a collection of over 80 galaxies bound together by gravity. The Local Group spans about 10 million light-years and includes 3 large spiral galaxies: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy, along with dozens of smaller dwarf galaxies that orbit the larger ones, like moons around planets. The Andromeda Galaxy, also known as M31, is the largest member of the Local Group. It contains roughly 1 trillion stars, more than twice the number in the Milky Way. Andromeda lies 2.5 million light-years from us, a distance so vast that the light we see from it tonight left the galaxy 2.5 million years ago, long before modern humans walked the Earth. Despite this distance, Andromeda is approaching the Milky Way at about 68 miles per second, roughly 250,000 miles per hour. The two galaxies are on a collision course, pulled together by mutual gravitational attraction. In approximately 4.5 billion years, Andromeda and the Milky Way will collide. This will not be a violent crash in the sense of physical impacts. Galaxies are mostly empty space. The stars within them are so widely separated that even when two galaxies merge, individual stars almost never collide. Instead, the galaxies will pass through each other, their structures distorted by gravitational forces. Spiral arms will warp and stretch. Stars will be flung into new orbits. Some stars will be ejected entirely, cast into intergalactic space. Over hundreds of millions of years, the two galaxies will merge, their central black holes eventually combining, creating a single giant elliptical galaxy. Astronomers have already coined a name for this future galaxy: Milkomeda. The Triangulum Galaxy, also known as M33, is the third largest member of the Local Group, containing perhaps 40 billion stars. It lies about 3 million light-years from the Milky Way. Triangulum may eventually be pulled into the Andromeda-Milky Way merger, adding its mass to the mix. The dozens of dwarf galaxies in the Local Group are much smaller, containing anywhere from a few million to a few billion stars. Many of these dwarfs are satellite galaxies, orbiting the larger spirals. The Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light, are dwarf galaxies orbiting the Milky Way. The Local Group, in turn, sits on the outskirts of the Virgo supercluster, also called the Local Supercluster, a massive collection of galaxy groups and clusters spanning about 110 million light-years. At the heart of this supercluster lies the Virgo cluster, a concentration of over 1,300 galaxies located about 54 million light-years from Earth. The Virgo cluster is so massive, containing a total mass of over 1,000 trillion suns, that its gravity influences the motion of galaxies across the entire supercluster. The Milky Way and the Local Group are falling toward the Virgo cluster, pulled by its immense gravitational attraction. But even the Virgo supercluster is not the top of the hierarchy. In 2014, astronomers using sophisticated mapping techniques defined a new structure called Laniakea, a supercluster of superclusters. Laniakea spans 520 million light-years and contains about 100,000 galaxies with a total mass of 100 million billion suns. The name Laniakea comes from Hawaiian and means immeasurable heaven, a fitting name for a structure of such staggering scale. Laniakea is defined not just by the spatial distribution of galaxies, but by their motion. Galaxies within Laniakea are all flowing toward a common center of mass, called the Great Attractor, a gravitational anomaly that pulls on everything in the local universe. The Great Attractor itself lies in the direction of the Hydra and Centaurus constellations, obscured by the disk of the Milky Way, making it difficult to observe directly, but its gravitational influence is unmistakable. The Milky Way, along with millions of other galaxies, is falling toward the Great Attractor at hundreds of miles per second, and Laniakea itself is being pulled toward an even larger concentration of mass. The Shapley supercluster, located about 650 million light-years from Earth, is one of the most massive structures in the nearby universe, containing tens of thousands of galaxies. The gravitational pull of the Shapley supercluster affects the motion of galaxies across billions of light-years. We are not just moving through space, we are being pulled, along with countless other galaxies, toward regions of higher and higher density, participating in a cosmic flow that has been ongoing for billions of years. This is our address in the cosmos: Earth orbiting the Sun, in the Orion arm of the Milky Way galaxy, in the local group, on the edge of the Virgo supercluster, within Laniakea, moving through space at over 1 million miles per hour, pulled by gravitational forces so vast they shape the motion of superclusters. The observable universe contains an estimated 2 trillion galaxies. Let that number rest in your mind for a moment. 2 trillion. Not 2 trillion stars, though the stars number far higher still. 2 trillion galaxies, each one a collection of hundreds of millions or billions or even trillions of stars. If you could count one galaxy per second, you would need over 63,000 years to count them all, working continuously without pause, without sleep, without rest. And remember, we're only counting structures visible from Earth within our cosmic horizon. The total number of galaxies in the whole universe, if the universe is infinite, could also be infinite. Galaxies come in bewildering variety. Spiral galaxies like the Milky Way and Andromeda display sweeping arms of stars and gas rotating around a central bulge. The spiral arms are regions of active star formation, where dense clouds of gas collapse under their own gravity to create new stars. These arms glow brightly with young, hot, blue stars and are illuminated by the light of stellar nurseries. Elliptical galaxies, shaped like stretched spheres or footballs, contain older stars and little gas for new star formation. They formed through the merger of smaller galaxies, collisions that stirred the stars into random orbits, rather than the organized rotation of a disk. Irregular galaxies have chaotic structures, often the result of gravitational interactions or collisions with other galaxies. They lack the symmetry of spirals or ellipticals and appear as amorphous clumps of stars and gas. The Large and Small Magellanic Clouds are examples of irregular galaxies, their structures distorted by the gravitational pull of the Milky Way. Then there are lenticular galaxies, disc-shaped but without spiral arms, transitional forms between spirals and ellipticals. And peculiar galaxies, warped or distorted by nearby gravitational forces, their shapes twisted into strange configurations by interactions with neighbours. Some galaxies shine brilliantly with active galactic nuclei, supermassive black holes at their centres consuming matter and spewing jets of radiation across millions of light-years. These quasars and blazars are among the most luminous objects in the universe, visible across billions of light-years. Others sit quiet and dim, their star formation long extinguished, their gas consumed or expelled, their remaining stars slowly fading as they age. Some galaxies are so faint and diffuse they are called ghost galaxies, ultra-diffuse galaxies that contain few stars spread across enormous volumes. The distribution of galaxies is not random. Galaxies cluster together, drawn by mutual gravitational attraction. Galaxy clusters are collections of hundreds or thousands of galaxies bound by gravity, surrounded by hot gas and held together by dark matter, the mysterious substance that makes up about 85% of all matter in the universe but does not emit, absorb, or reflect light. The Coma cluster contains over 1,000 known galaxies. The Virgo cluster contains more than 1,300. These clusters in turn group into superclusters, and superclusters connect along vast filaments, cosmic threads of matter stretching across hundreds of millions of light-years. In cosmology, galaxy filaments are the largest known structures in the universe. These massive thread-like formations are composed of walls of galactic superclusters connected by bridges of galaxies, gas, and dark matter. They commonly reach 160 to 260 million light-years in length, and some stretch far beyond that. The cosmic web, as this structure is known, resembles a three-dimensional foam or sponge. Dense filaments and walls surround enormous voids. Where filaments intersect, they form nodes of exceptional density, rich clusters of thousands of galaxies packed into relatively small volumes. Between these bright threads lies darkness, the voids, where galaxies are scarce and space is truly empty. The cosmic web is not a static structure. It grew over billions of years from tiny density variations in the early universe. In the first moments after the Big Bang, quantum fluctuations created regions that were slightly denser than average and regions that were slightly less dense. These differences were minuscule, perhaps 1 part in 100,000. But gravity amplifies even tiny advantages. Denser regions pulled in more matter from their surroundings, making them denser still. This created a positive feedback loop. The denser a region became, the more strongly it pulled matter toward itself. Over millions of years, these small clumps merged into larger clumps, which merged into galaxies, which merged into clusters, which aligned into filaments. Meanwhile, regions that started slightly less dense lost matter to their denser neighbours. As matter drained away toward the collapsing overdense regions, the underdense regions became emptier and emptier, expanding into voids. The process is called gravitational instability, and it turned barely perceptible initial ripples into the dramatic large-scale structure we observe today. One of the most famous large-scale structures is the Sloan Great Wall, discovered in 2003 during the Sloan Digital Sky Survey. This wall of galaxies measures about 1.37 billion light-years in length. It is a flat sheet, a vast surface upon which galaxies cluster, separated from other structures by voids hundreds of millions of light-years wide. The wall is not a solid object. It is a concentration of galaxies, a region where thousands upon thousands of galaxies have accumulated over billions of years, drawn together by gravity into a coherent structure. Another massive structure is the CFA2 Great Wall, discovered in 1989 during the Second Center for Astrophysics Redshift Survey. This wall stretches roughly 750 million light-years in length and 250 million light-years in width, but it is only about 20 million light-years thick. Picture a vast cosmic sheet, a wall of galaxies extending across a significant fraction of the observable universe. These walls are not dense. Galaxies within them are still separated by millions of light-years, but compared to the voids that surround them, walls represent regions of higher than average density. Recently, astronomers discovered Quipu, a structure that may be the largest in the known universe in terms of length. Quipu spans approximately 1.3 billion light-years, more than 13,000 times the diameter of the Milky Way. Its mass is 200 quadrillion times that of the Sun. To write that mass in kilograms would require a number with 45 digits. Quipu is not a single entity but a superstructure, a cluster of galaxy clusters connected by filaments, a main strand with many branches extending from it, resembling the Incan Quipu knotted strings used for record keeping, hence the name. Quipu and 4 other similar structures together encompass 30% of the galaxies, 45% of the galaxy clusters, 25% of the matter, and 13% of the overall volume within their observed region of the universe. These 5 superstructures, identified within a range of 425 million to 815 million light-years from Earth, include the Shapley supercluster, previously considered the largest structure in the local universe, the Serpens Corona Borealis superstructure, the Hercules supercluster, and the Sculptor-Pegasus superstructure, which stretches between the constellations Sculptor and Pegasus. But even Quipu may not hold the title of largest structure for long. The Hercules Corona Borealis Great Wall, discovered in 2013 through observations of gamma-ray bursts, is estimated to span more than 10 billion light-years across. If confirmed, this would make it the single largest known structure in the observable universe, extending across more than 10% of the observable cosmos. Its existence is controversial. A structure 10 billion light-years across challenges the cosmological principle, the foundational assumption that the universe should be roughly homogeneous and isotropic on large scales. According to the cosmological principle, when you average over sufficiently large volumes, the universe should look the same in every direction and from every location. This principle has been remarkably successful in cosmology, allowing scientists to apply the same physical laws everywhere and to develop models of cosmic evolution that work across vast distances and times. But a structure 10 billion light-years across represents such a significant departure from the average density that some scientists question whether it truly exists as a coherent structure or whether it is a statistical artifact, a random alignment of galaxy clusters that appears connected but is not gravitationally bound. The debate over the Hercules Corona Borealis Great Wall highlights a deeper question. How large can structures in the universe grow? Is there a maximum size beyond which gravity cannot organize matter into coherent structures? Dark energy, the mysterious force accelerating cosmic expansion, may provide an answer. On the larger scales, dark energy dominates over gravity. It prevents matter from collapsing into structures larger than a few billion light-years. The cosmic web, with its filaments and voids, may represent the larger scale on which the universe can organize itself. These structures reveal the fundamental architecture of the cosmos. The universe is not a smooth distribution of matter. It is a foam, a web, a network of dense filaments surrounding vast empty regions. Understanding this architecture is crucial to understanding cosmic evolution, the formation of galaxies, and even the ultimate fate of the universe. Cosmic voids occupy roughly 90% of the volume of space. These are not truly empty, but they are profoundly underdense. A typical region of space, averaged over very large scales, might contain 10 galaxies in a given volume. The same volume in a void might contain only 1 or 2 galaxies, or sometimes none at all. The density of matter in voids is about 10 to 20% of the cosmic average. Between the rare galaxies in voids stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas left over from the Big Bang. Without enough mass to pull things together, structure formation essentially stops in voids. Gravity is too weak. No new galaxy clusters can form. No rich superclusters emerge. The void stays a void, and in fact, voids grow over time. As the universe expands, voids expand faster than the cosmic average because they lack the gravitational pull that slows expansion in denser regions. Dark energy accelerates this process. In voids, where matter is sparse, dark energy dominates, pushing space apart at an ever-increasing rate. The voids grow like bubbles, swelling larger and larger, eating into the filaments that surround them. The largest known void, the Eridanus supervoid, discovered through its impact on the cosmic microwave background, measures roughly 1.8 billion light-years across. This void is so enormous, so profoundly empty that light from the cosmic microwave background, the faint afterglow of the Big Bang, cools slightly as it passes through. The reduced gravity in the void causes less gravitational interaction with the photons, and the expansion of the void itself stretches their wavelength, showing up as a cold spot in temperature maps of the early universe. If you were somehow transported to the center of such a void, you would find yourself in one of the loneliest places in the cosmos. Look in any direction, and you would see very few galaxies. The night sky would be profoundly dark, with only scattered points of light visible against the blackness. The nearest galaxy might be tens or hundreds of millions of light-years away. You would be surrounded by emptiness, adrift in a cosmic desert where matter is exceedingly rare. The cosmic web, with its filaments and voids, represents the largest scale on which the universe exhibits structure. Beyond this, on scales larger than a few billion light-years, the universe becomes smooth. Density variations average out. No structures will ever form at these scales because dark energy, the mysterious force accelerating cosmic expansion, dominates over gravity. The universe is expanding and the expansion is accelerating. In the far future, billions of years from now, this expansion will continue to stretch space, thinning the filaments and enlarging the voids until galaxies become isolated islands separated by ever-growing darkness. The observable universe is not infinite, which means we can, in theory, count its contents. The numbers are absurd, but they are finite. Let us begin with stars, the bright furnaces where matter is transmuted, where hydrogen fuses into helium, where the elements of the periodic table are forged. Astronomers estimate there are between 1 sextillion and 1 septillion stars in the observable universe. 1 sextillion is 10 to the power of 21. 1 septillion is 10 to the power of 24. The actual number likely falls somewhere in between, around 10 to the power of 24, 1 followed by 24 zeros. To write it out, 1 sextillion 000 stars. If you started counting one star per second at the moment of the Big Bang 13.8 billion years ago, you would still be counting today, and you would not finish for another 13 billion years beyond that. The task would require over 30 billion years of continuous counting, more than twice the current age of the universe, and you would still be counting stars only in the observable universe, ignoring the potentially infinite number beyond our cosmic horizon. Each star is a world unto itself, a sphere of plasma held together by its own gravity, powered by nuclear fusion at its core. Stars come in many types. Red dwarfs, the smallest and most common stars, contain just a fraction of the Sun's mass and burn so slowly they will last for trillions of years. Blue giants, massive and hot, burn through their fuel in mere millions of years before exploding as supernovae. White dwarfs, the remnants of sun-like stars, are dense and dim, slowly cooling over billions of years. Neutron stars, the collapsed cores of massive stars, pack more mass than the Sun into a sphere just 20 kilometers across. Black holes, the ultimate endpoint of stellar evolution for the most massive stars, warp space-time so severely that nothing, not even light, can escape. But stars are only part of the inventory. The universe also contains planets, moons, asteroids, comets, clouds of gas and dust, rogue planets drifting through interstellar space, brown dwarfs too small to sustain fusion, and countless other objects. Recent discoveries suggest that planets are incredibly common. Nearly every star hosts at least one planet, and many host multiple planets. If every star has even one planet, that means there are at least 10 to the power of 24 planets in the observable universe, a number equal to the number of stars. Some of these planets are rocky worlds like Earth. Others are gas giants like Jupiter. Some orbit close to their stars, scorched and airless. Others orbit in the habitable zone where temperatures might allow liquid water to exist. A few might harbour life, simple or complex, familiar or utterly alien. The sheer number of planets suggests that Earth is almost certainly not unique. Life may be rare, but in a universe with 10 to the power of 24 planets, even rare events occur trillions upon trillions of times. And then there are the atoms themselves, the fundamental building blocks of matter. How many atoms exist in the observable universe? Calculations, based on estimates of the universe's mass and composition, yield a number of roughly 10 to the power of 82 atoms. That is a 1 followed by 82 zeros. 10 sextillion 000 000 000 000 000 000 000 000 atoms. To put this in context, the number of atoms in the observable universe is larger than the number of stars by a factor of about 100 billion trillion. A single grain of sand, barely visible to the naked eye, contains approximately 50 quintillion atoms, which is 50 billion billion. The human body contains roughly 7 octillion atoms, which is 7 billion billion billion. All the atoms in all the humans who have ever lived, roughly 100 billion people over the entire history of our species, would total around 700 nonillion atoms, a number so small compared to the cosmic total that it barely registers. You could take every atom in every human who has ever existed and lose them entirely in the cosmic inventory, like dropping a handful of sand into the Sahara Desert. The observable universe is estimated to have a mass of about 1.5 times 10 to the power of 53 kilograms, which is 1.5 followed by 53 zeros in kilograms. Most of this mass is hydrogen and helium, the simplest and most abundant elements. Created in the first few minutes after the Big Bang during a period called Big Bang nucleosynthesis, hydrogen accounts for about 92.68% of all atoms in the universe. Helium makes up roughly 7.15%. Everything else, all the heavier elements like carbon, oxygen, nitrogen, silicon, iron, gold, uranium, the elements that make up planets and life and technology, constitute less than 0.5% of the total atom count. We are made of stardust, but that stardust is exceedingly rare in the cosmic inventory. Carbon, the foundation of organic chemistry and life as we know it, makes up only about 0.03% of all atoms. Oxygen, essential for water and for respiration, accounts for about 0.06%. Iron, the most common element in Earth's core and in the cores of many planets, is only about 0.003% of cosmic atoms. These heavier elements are created inside stars through nuclear fusion and are scattered into space when stars die, either gently shedding their outer layers as planetary nebulae or violently exploding as supernovae. It takes billions of years for the universe to accumulate even a tiny fraction of heavy elements. The early universe, shortly after the Big Bang, contained almost no heavy elements at all, just hydrogen and helium and trace amounts of lithium. The distribution of matter is not uniform. Most atoms are concentrated in stars and galaxies, packed into the filaments and clusters of the cosmic web. The voids, occupying 90% of the volume, contain far fewer atoms per cubic meter. On average, there is about 1 hydrogen atom per cubic meter of space, when averaged across the entire observable universe. But this average conceals enormous variations. In dense regions like the core of a star, the density can reach 150 grams per cubic centimeter, billions of times denser than lead. The Sun's core, where hydrogen fuses into helium at temperatures of 15 million degrees Celsius, has a density about 150 times that of water. In the voids, the density might drop to 1 atom per 10 cubic meters or less, a near-perfect vacuum better than anything we can create in laboratories on Earth. Interstellar space within galaxies typically contains about 1 atom per cubic centimeter. Intergalactic space, the vast darkness between galaxies, contains perhaps 1 atom per cubic meter. The universe is lumpy, with matter clumped into structures separated by vast expanses of near vacuum. These numbers, as large as they are, still represent only what we can observe. The total universe, if it extends beyond our cosmic horizon, could contain vastly more. If the universe is infinite, then the number of atoms is also infinite, as is the number of stars and galaxies. If the universe is merely 250 times larger than the observable portion, as some estimates suggest, then the total number of atoms would be 250 cubed times larger, which is 15,625,000 times as many, pushing the total to a number with over 88 digits. If the universe is 10 to the power of 23 times larger, as inflationary theory might suggest, then the number of atoms becomes so incomprehensibly vast that even scientific notation struggles to express it meaningfully. The mind struggles to grasp quantities on this scale. They cease to have intuitive meaning. They become abstractions, symbols on a page, representations of a reality too large for human comprehension. We can calculate these numbers, we can write them down, we can compare them mathematically, but we cannot truly imagine what 10 to the power of 82 atoms looks like. Our brains did not evolve to process such quantities. We evolved to count small numbers, to track herds of a few dozen animals, to gather groups of fruits, to navigate landscapes measured in kilometers. Cosmic quantities are beyond our intuitive grasp, accessible only through mathematics and analogy. We have journeyed outward, from Earth to the edge of the observable universe, crossing scales of billions of light years and encountering trillions of galaxies and sextillions of stars and 10 to the power of 82 atoms. Now we reverse course. We descend scale by scale into the realm of the very small. And we will discover that the universe is just as strange and incomprehensible at the smallest scales as it is at the largest. The journey inward is a journey into increasing strangeness, where the familiar rules of macroscopic physics give way to the bizarre laws of quantum mechanics. A human being stands roughly 1.7 meters tall. We are made of cells, roughly 37 trillion of them, an estimate that varies depending on body size and composition. Most of these cells are blood cells, red blood cells that carry oxygen and white blood cells that fight infection, circulating through our veins and arteries. But trillions more compose our muscles, bones, organs, skin, and nervous system. And living alongside our own cells in a complex symbiotic relationship are approximately 39 trillion bacterial cells, single-celled organisms that inhabit our digestive system and skin, helping digest food, synthesize vitamins, and protect against harmful pathogens. We are, in a sense, ecosystems, collections of trillions of individual living units working in concert, a community of organisms cooperating to create what we call a human being. A typical human cell measures about 10 micrometers in diameter, though sizes vary widely. A micrometer is 1/1,000,000th of a meter. 10 micrometers is 100,000 times smaller than the height of a human. If you could shrink yourself down to the size of a cell, a human body would tower above you like a continent-sized structure, incomprehensibly vast, stretching beyond the horizon in all directions. From this perspective, blood vessels would appear as immense tunnels through which you could travel. Muscles would loom as massive fibre bundles, and bones would be colossal scaffolding supporting the entire architecture. Inside each cell is a universe of complexity. The nucleus, typically about 6 micrometers in diameter, contains DNA, the molecule that encodes genetic information. Surrounding the nucleus are various organelles, specialized structures that perform different functions. Mitochondria, the powerhouses of the cell, generate energy by breaking down glucose through a process called cellular respiration. A single cell might contain hundreds or even thousands of mitochondria. Ribosomes, tiny structures that read messenger RNA and assemble proteins, number in the hundreds of thousands per cell. The endoplasmic reticulum, a network of membranes, helps fold and transport proteins. The Golgi apparatus packages molecules for export. Lysosomes break down waste materials. The complexity within a single cell rivals the complexity of a city, with different structures performing different functions, all coordinated through chemical signals and feedback loops. DNA, deoxyribonucleic acid, the molecule that carries genetic information, is a double helix, a twisted ladder with rungs made of chemical base pairs. The width of a DNA molecule is about 2 nanometers. A nanometer is 1/1000th of a meter. DNA is 5,000 times smaller than the cell that contains it. Yet if you could unwind all the DNA in a single human cell and stretch it out in a line, it would measure about 2 meters long, longer than the height of most humans. This is possible because DNA is coiled and compacted with extraordinary efficiency. Wrapped around proteins called histones, coiled into chromatin, and then compacted further into chromosomes. A human cell contains 46 chromosomes, 23 inherited from each parent, and together they contain about 3 billion base pairs, the chemical letters that spell out the instructions for building and operating a human being. Now we descend further, past cells and into the realm of molecules. Molecules are groups of atoms bonded together by electromagnetic forces. Water, H2O, one of the simplest and most essential molecules, consists of 2 hydrogen atoms bonded to 1 oxygen atom. The molecule measures about 0.3 nanometers across. Water is the solvent of life, the medium in which biochemical reactions occur, the fluid that fills our cells and flows through our blood. About 60% of the human body is water. In the brain, the proportion is even higher, about 75%. Proteins, the workhorses of the cell, are chains of amino acids folded into complex 3-dimensional shapes. Some proteins are small, containing just a few dozen amino acids. Others are enormous, containing thousands of amino acids and measuring tens of nanometers in length. Proteins perform an astonishing variety of functions. Enzymes are proteins that catalyze chemical reactions, speeding up processes that would otherwise take years or centuries to occur spontaneously. Structural proteins like collagen provide mechanical support, forming the scaffolding of tissues. Transport proteins like hemoglobin carry molecules through the body. Antibodies are proteins that recognize and neutralize foreign invaders. The human body contains tens of thousands of different types of proteins, each precisely shaped to perform its specific function. Molecules are not solid objects in the way we typically imagine solidity. They are collections of atoms held together by electromagnetic forces. By the sharing or transfer of electrons, the atoms vibrate and rotate. The bonds between them bend and stretch. A molecule is a dynamic structure, constantly in motion, constantly interacting with its environment. An atom is astonishingly small. The diameter of a hydrogen atom, the simplest and smallest atom, is about 0.1 nanometers, 1/10 billionth of a meter. Atoms are mostly empty space. At the center of an atom is the nucleus, composed of protons and neutrons, collectively called nucleons. The nucleus measures about 10 femtometers in diameter. A femtometer, sometimes called a fermi, is 1 quadrillionth of a meter, 10 to the power of minus 15 meters. To understand just how empty an atom is, imagine scaling it up. If you enlarged an atom until it was the size of a football stadium, the nucleus would be a marble at the centre of the field, perhaps a centimetre across. The rest of the stadium, the seating, the concourse, the entire volume out to the walls would be empty space, with electrons existing as probability clouds somewhere in that vast emptiness. This is not a metaphor. Atoms genuinely are this empty. The solid matter we perceive, the desk beneath your hands, the ground beneath your feet, is mostly nothing, just electromagnetic forces preventing the electron clouds of different atoms from overlapping. Electrons are fundamental particles as far as we know. They have no internal structure that we have been able to detect. They are treated as point-like in the standard model of particle physics, meaning they have no spatial extent, no size at all. Experiments have probed down to scales of about 10 to the power of minus 22 meters without finding any internal structure to electrons. For all practical purposes, an electron is a point of charge and mass existing in a probability cloud around the nucleus. Electrons have mass, about 9.109 times 10 to the power of minus 31 kilograms, an incomprehensibly tiny amount. It would take about 2 trillion electrons to equal the mass of a single grain of sand. Electrons carry a negative electric charge, and this charge is what binds them to the nucleus. The electromagnetic force between the negatively charged electrons and the positively charged nucleus is what holds the atom together. Electrons do not orbit the nucleus in fixed paths like planets around a star. That early model of the atom, the Bohr model, is a useful simplification but not accurate. Instead, electrons occupy probability clouds called orbitals. An orbital is a region of space where the electron is likely to be found. The electron does not have a definite position until it is measured. Until then, it exists in a superposition, spread out across the entire orbital, simultaneously everywhere and nowhere. This is one of the strange consequences of quantum mechanics, the theory that governs the behavior of matter and energy at small scales. The nucleus contains protons and neutrons. A proton has a positive electric charge equal in magnitude to the electron's negative charge. A proton has a mass about 1,836 times that of an electron. A neutron has no charge and a slightly larger mass than a proton, about 1,839 times the electron's mass. The number of protons in the nucleus defines the element. Hydrogen has 1 proton, helium has 2, carbon has 6, oxygen has 8, iron has 26, gold has 79, uranium has 92. The number of neutrons can vary, creating different isotopes of the same element. Carbon-12 has 6 neutrons, carbon-14 has 8 neutrons, but protons and neutrons are not fundamental particles. They are made of quarks, bound together by the strong nuclear force, one of the 4 fundamental forces of nature. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Quarks are held together by particles called gluons, which mediate the strong force. The strong force is extraordinarily powerful, but operates only over distances comparable to the size of a nucleus. Beyond a distance of a few femtometers, the strong force becomes negligible. Within the nucleus, it is strong enough to overcome the electromagnetic repulsion between positively charged protons, binding them together despite their mutual repulsion. Quarks are among the smallest things we've ever detected. Experiments at particle accelerators like the Large Hadron Collider have probed down to scales of about 10 to the power of minus 19 meters without finding any internal structure to quarks. They appear to be point-like, fundamental particles, elementary constituents of matter. There are 6 types of quarks, known as flavors: up, down, charm, strange top, and bottom. The up and down quarks are the lightest and most stable, composing the protons and neutrons in ordinary matter. The others, charm, strange, top and bottom, are heavier and exist only fleetingly in high-energy collisions before decaying into lighter particles. The standard model of particle physics describes the fundamental particles and forces that govern the universe at the smallest scales. It includes 12 matter particles, 6 quarks and 6 leptons. The leptons include the electron, the muon, the tau, and 3 types of neutrinos. It also includes force-carrying particles, photons, which mediate electromagnetism, W and Z bosons, which mediate the weak nuclear force, gluons, which mediate the strong force, and the Higgs boson, which gives other particles mass. Gravity, the 4th fundamental force, is not yet fully integrated into the standard model. It is described by Einstein's general relativity, which treats gravity as the curvature of space-time rather than as a force mediated by particles, though physicists theorize a particle called the graviton might exist to carry the gravitational force at the quantum level. We have descended from the scale of a human, 1.7 meters, down to the scale of quarks, about 10 to the power of minus 19 meters. That is a journey across roughly 19 orders of magnitude, a factor of 10 billion billion. If you could magnify a quark to the size of a human, an actual human would tower over it by the same factor that the observable universe towers over a human. The very small and the very large are mirror extremes, equally distant from our everyday experience, equally inaccessible to direct intuition. Quarks and electrons are the smallest confirmed particles, the elementary particles of the standard model that have no known substructure. But physics does not stop there. Theoretical frameworks suggest the possibility of even smaller scales, structures, or entities that exist at the very edge of what the laws of physics allow, perhaps even beyond what those laws can describe. We now enter the realm of the speculative, the unproven, the boundary where measurement fails and mathematics becomes our only guide. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, one-dimensional loops or strands of energy called strings. These strings are incomprehensibly small, on the order of the Planck length, about 1.616 times 10 to the power of minus 35 meters. That is 10 million billion times smaller than the size of a proton. To put this in perspective, if you scaled an atom up to the size of the solar system, the distance from the Sun to Neptune, a string would be about the size of a tree on Earth. In string theory, the different particles we observe, electrons, quarks, photons, neutrinos, W and Z bosons, gluons, all of them, are not distinct entities with independent existence. Instead, they are different vibrational modes of the same fundamental string. Just as a guitar string can vibrate at different frequencies to produce different musical notes, a fundamental string can vibrate in different ways to produce different particles. The mass, charge, spin, and other properties of a particle arise from the specific vibrational pattern of the string. An electron is a string vibrating one way. A quark is the same string vibrating a different way. A photon is another vibrational mode. All particles are fundamentally the same thing, just strings vibrating in different patterns. String theory is mathematically elegant and has the potential to unify all the fundamental forces of nature into a single framework, something physicists have sought for over a century. Einstein spent the last decades of his life searching for a unified field theory, an equation that would describe electromagnetism and gravity together. He did not succeed. String theory offers a potential solution, a framework that includes gravity, electromagnetism, the strong force, and the weak force all in one consistent mathematical structure. But string theory has a problem, or rather several problems. First, it requires the existence of extra spatial dimensions beyond the 3 we experience. Most versions of string theory require 10 dimensions in total, 9 spatial dimensions and 1 time dimension. The extra 6 spatial dimensions must be compactified, curled up into shapes so small that we cannot detect them. These compactified dimensions might be on the scale of the Planck length, which is why we have never observed them. From our macroscopic perspective, space appears 3-dimensional, but at the smallest scales it might curve and fold into higher dimensions. Second, string theory has not yet made any testable predictions that could be verified experimentally. It operates at energy scales far beyond what current particle accelerators can reach. The Large Hadron Collider, the most powerful particle accelerator ever built, can probe energies up to about 14 tera-electron volts. To test string theory directly, we would need energies on the order of the Planck energy, about 10 to the power of 19 giga-electron volts, a factor of over a quadrillion times higher. Building an accelerator powerful enough to reach those energies is far beyond current technology. Such a machine would need to be larger than the solar system. Because string theory cannot be tested directly, it remains speculative. Some physicists view it as the most promising candidate for a theory of everything. Others criticize it as untestable and therefore not truly scientific. The debate continues, but string theory has nonetheless led to profound insights in mathematics and theoretical physics, even if it has not yet been confirmed or falsified by experiment. The Planck length represents a fundamental limit in physics, the smallest meaningful distance in the universe. It is defined by combining 3 fundamental constants: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. The Planck length is about 1.616 times 10 to the power of minus 35 meters. Below this scale, the concepts of space and time as we understand them likely break down completely. Quantum fluctuations of space-time become so violent, so extreme, that the smooth fabric of reality dissolves into a froth, a quantum foam where distance and duration lose meaning. Physicist John Wheeler introduced the concept of quantum foam in the 1950s. He suggested that at the Planck scale, space-time is not smooth and continuous but turbulent and chaotic, filled with fleeting fluctuations. At this scale, the certainty and predictability of classical physics vanish entirely. Virtual particles and antiparticles pop in and out of existence, borrowing energy from the vacuum for infinitesimal fractions of a second before annihilating each other. These virtual particles are not merely theoretical abstractions. They have measurable effects. They influence the energy levels of atoms, creating tiny shifts in spectral lines that have been confirmed experimentally. They contribute to the vacuum energy, the inherent energy of empty space itself. The vacuum in quantum field theory is not empty. It is a seething sea of activity, invisible and inaccessible to direct observation, but essential to the functioning of the universe. The vacuum energy creates a pressure, a kind of negative gravity that may be connected to dark energy, the mysterious force accelerating the expansion of the universe. Understanding the vacuum at the quantum level is one of the great challenges of theoretical physics. Attempts to measure anything smaller than the Planck length encounter a fundamental paradox. To probe such small distances, you would need to concentrate enormous amounts of energy into a tiny region. According to the Heisenberg uncertainty principle, measuring a smaller distance requires using particles with higher energy and thus shorter wavelength. But there is a limit. If you concentrate enough energy into a region smaller than the Planck length, the energy density becomes so high that it collapses into a black hole, making the measurement impossible. The Planck length may represent not just a practical limit but a fundamental one. A grain of space-time beyond which the universe does not subdivide further. If space-time itself is quantized, made of discrete units rather than being continuous, then the Planck length is the size of those units. Space would not be infinitely divisible. It would be pixelated, a grid of unimaginably tiny cells, each one a Planck length across. Time, similarly, would be quantized into units of Planck time, about 5.39 times 10 to the power of minus 44 seconds, the time it takes light to travel one Planck length. Below the Planck time, the notion of before and after might not even make sense. Some physicists have speculated about entities even smaller than strings, theoretical particles called prions that might compose quarks and leptons. In this view, quarks and electrons are not fundamental but are themselves made of smaller constituents. Various prion models have been proposed over the years, but none have gained wide acceptance, largely because there is no experimental evidence for them. The standard model treats quarks and leptons as fundamental, and so far, experiments have found no reason to doubt that assumption. Prions remain a speculative idea, an answer to a question that may not need answering. For now, the Planck length stands as the frontier of the infinitesimally small, the edge of the knowable, the point where our theories falter and the universe guards its deepest secrets. We have journeyed from the scale of a human down through cells and molecules and atoms and nuclei and quarks to the very limit of what physics can describe. Beyond this point lies terra incognita, a realm where space and time may not exist as we understand them, where the rules change in ways we cannot yet imagine. The scale of a human being, roughly 1 to 2 meters, sits in a peculiar position within the vast range of scales the universe offers. On a logarithmic scale, which measures orders of magnitude rather than linear distance, humans are almost exactly in the middle between the smallest and largest scales in the cosmos. The Planck length, the smallest meaningful distance, is about 10 to the power of minus 35 meters. The observable universe is about 10 to the power of 27 meters across. A human, at about 1 meter, is 10 to the power of 0 meters. We sit roughly 35 orders of magnitude above the Planck length and 27 orders of magnitude below the size of the observable universe. This positioning is more than a mathematical curiosity. It reflects the nature of the universe itself and the physics that governs it, the reasons why structures at different scales form and persist, why complexity arises where it does. Atoms bond together to form molecules because of the electromagnetic force, the attraction between positively charged nuclei and negatively charged electrons, balanced by the repulsion between like charges. Molecules assemble into cells because of chemical interactions, hydrogen bonds, van der Waals forces, and the principles of thermodynamics that favour certain configurations over others. Cells organise into multicellular organisms because natural selection favours cooperation and specialisation. Complex life emerges at scales where quantum effects are mostly irrelevant and gravitational effects are weak. We exist at a scale where chemistry works, where structures can be stable, where evolution can operate over billions of years. If humans were much smaller, if we existed at the scale of molecules or atoms, quantum uncertainty would dominate our experience. Our bodies would flicker in and out of existence. Electrons would tunnel through barriers, appearing on the other side without crossing the intervening space. The probabilistic nature of quantum mechanics would prevent the kind of stable, deterministic structures that life requires. The laws of quantum mechanics allow for superposition, where a particle exists in multiple states simultaneously until measured. At human scales, quantum superpositions average out. The immense number of particles involved, trillions upon trillions of atoms, ensures that quantum randomness cancels out and classical predictable behaviour emerges. But shrink down to atomic scales, and that predictability vanishes. The world becomes probabilistic, strange, fundamentally uncertain. If humans were much larger, if we existed at the scale of planets or stars, gravity would dominate. A creature the size of a planet could not hold its shape against its own gravitational pull. Gravity scales with mass. Double the size of an object in all 3 dimensions, and you increase its volume by a factor of 8, meaning 8 times the mass. But surface area only increases by a factor of 4. Structural strength depends on cross-sectional area, so it scales with the square of size, while gravitational force scales with mass, which scales with the cube of size. As objects grow larger, gravity becomes stronger relative to structural forces. A creature the size of Earth would collapse under its own weight. Its internal pressure would compress matter into denser and denser states. If it grew large enough, nuclear fusion would ignite in its core and it would become a star. Stars exist in a delicate balance between gravity, which tries to crush them, and radiation pressure from fusion, which pushes outward. Stars can grow to enormous sizes, hundreds of times the diameter of the Sun, but even they have limits. Above a certain mass, roughly 150 to 300 times the mass of the Sun depending on composition, stars become unstable and tear themselves apart. The scale at which we exist, the human scale, is the scale where complexity is possible, where the laws of chemistry and biology can operate, where structures can form that are neither dominated by quantum uncertainty nor crushed by their own gravity. It is no accident that life emerged at this scale. Life could not exist at the scale of atoms or stars. The physics would not allow it. We exist where we must exist for existence itself to be possible in the forms we recognize. From our vantage point, both the very large and the very small are inaccessible, beyond the reach of direct perception. We cannot travel to distant galaxies, not with current technology and perhaps not ever, given the speed of light and the expansion of space. We cannot see atoms with the naked eye. The wavelength of visible light, about 400 to 700 nanometers, is thousands of times larger than an atom. To see something, light must bounce off it, and if the wavelength of light is larger than the object, the light simply passes around it. We can build electron microscopes that use beams of electrons instead of light, achieving much higher resolution, and we can image individual atoms. But we cannot perceive them directly. We perceive the universe through a narrow window, the range of electromagnetic radiation our eyes detect, the range of temperatures our bodies tolerate, the range of timescales our brains process. Visible light is a tiny sliver of the electromagnetic spectrum spanning wavelengths from about 400 to 700 nanometers. Below that lies ultraviolet, then X-rays, then gamma rays, invisible to our eyes but detectable with instruments. Above visible light lies infrared, then microwaves, then radio waves stretching to wavelengths of meters or kilometers. Our eyes evolved to detect visible light because the sun emits most of its energy in that range, and because the Earth's atmosphere is transparent to those wavelengths. It is evolutionary happenstance, not fundamental necessity. A human lifetime is about 2.5 billion seconds, roughly 70 to 80 years. Processes faster than a fraction of a second are invisible to us without instruments. We cannot see individual frames in a movie which flashes by at 24 frames per second. We cannot perceive the vibrations of sound waves, which oscillate at hundreds or thousands of cycles per second. Chemical reactions in our cells occur on timescales of milliseconds to seconds. Processes slower than decades are too gradual to notice within a single human life. Continental drift proceeds at about 2 centimeters per year. We know it happens, but we cannot watch it. Evolutionary change, the gradual alteration of species over generations, occurs over thousands to millions of years. We see only a frozen snapshot, a single instant in the ongoing story of life. We evolve to perceive the world at human scales, and everything beyond that requires technology and imagination, instruments to extend our senses and mathematics to describe what we cannot see. Telescopes collect light from distant galaxies, revealing structure billions of light years away. Microscopes magnify the small, revealing the intricate machinery of cells. Particle accelerators smash atoms together at high energies, recreating conditions from the early universe and revealing the behavior of fundamental particles. But we are also observers, and this is extraordinary. We are the universe becoming aware of itself. Conscious minds made of atoms forged in the cores of dying stars, contemplating the cosmos from which we emerged. Hydrogen atoms, created in the Big Bang, fused into helium in stellar cores, then into carbon and oxygen and nitrogen in later generations of stars, scattered into space when those stars died, eventually coalescing into planets and, on at least one planet, into living things. You're made of stardust, and you're aware of this fact. You can contemplate your own origins, trace the lineage of your atoms back billions of years, understand the nuclear physics that create the elements in your body. The universe, through you, is observing itself, asking questions about its own nature, seeking to understand its own history and fate. The scale at which we exist is an accident of physics and evolution, but the fact that we exist at all, and that we can understand scales far removed from our own, is profound. We have built instruments that can see across billions of light years and probe down to scales a billion times smaller than an atom. We have developed mathematics to describe phenomena we cannot directly perceive and experiments to test theories about realms we cannot visit. We have mapped the cosmic web, counted galaxies, calculated the age of the universe, discovered the Higgs boson, imaged black holes, detected gravitational waves. From our modest position in the middle, we have managed to comprehend both the immense and the minute, to place ourselves within a framework that spans 62 orders of magnitude. Some argue that our position in the middle is significant in itself, that it suggests a kind of cosmic balance or purpose. Others see it as a selection effect, an inevitable consequence of the fact that observers capable of asking these questions must exist at scales where complexity is possible, where the laws of physics permit stable structures and the emergence of consciousness. The universe does not care where we sit on the scale of size. It offers no commentary, no explanation, no moral lesson. It simply is. We are here, midway between the Planck length and the cosmos, looking outward and inward, trying to comprehend a reality that extends in both directions far beyond the reach of intuition. The scale of the universe invites profound philosophical reflection. What does it mean to be a tiny collection of atoms on a small planet orbiting an average star, in an unremarkable galaxy in a vast cosmos that contains trillions of galaxies and will continue expanding for trillions of years after we're gone? Does the immensity of space render human life insignificant? Or does the fact that we can comprehend this immensity grant us a unique significance, a meaning that transcends mere size? The physicist Steven Weinberg once remarked that the more the universe seems comprehensible, the more it also seems pointless. His comment captures a certain modern existential anxiety. The cosmos, as revealed by science, operates according to impersonal laws. Stars burn not for any purpose, but because gravity compresses matter until temperatures and pressures become high enough for nuclear fusion to ignite. Galaxies collide not with intent, but because their mutual gravity pulls them together over hundreds of millions of years. The universe does not care whether we exist. It does not notice our achievements, our art, our science, our loves and losses. It does not witness our suffering or celebrate our triumphs. From a cosmic perspective, the entire history of humanity, from the first spark of consciousness to the last breath of the last human, is a fleeting moment, a brief flicker in an eternity of expanding space. And yet, some thinkers find meaning not despite this vastness, but because of it. The fact that the universe is so large and so old, and that we exist at all, is extraordinary. The conditions required for life are specific and delicate. Stars must form to create heavy elements through fusion and supernova. Planets must exist in habitable zones around those stars, orbits where temperatures allow liquid water to persist. Atmospheres must shield against harmful radiation. Geological activity must recycle nutrients and regulate climate. Evolution must have billions of years to produce complexity. All of these conditions have been met on Earth, and possibly elsewhere, but they are not guaranteed. The universe could have been lifeless, a vast expanse of hydrogen and helium gas cooling gradually toward absolute zero, with no stars, no planets, no complexity, no consciousness. But it is not. We are here. That is remarkable. Consciousness itself is perhaps the most remarkable phenomenon in the known universe. We are not merely matter, we are matter organized in such a way that it can reflect upon itself, that it can contemplate its own existence and the nature of reality. The atoms in your brain were forged in stars that exploded billions of years ago, scattering their contents into space, where they eventually coalesced into new stars and planets, and on at least one planet into living things. Those atoms have journeyed across the galaxy, survived supernovae, drifted through interstellar space, fallen onto a young Earth, been incorporated into rocks and water and air, and eventually, through the process of evolution, been organized into a structure capable of asking where it came from. You're made of stardust, and you're aware of this fact. You can trace the lineage of your atoms back through billions of years. You can understand the nuclear physics that created the carbon and oxygen and nitrogen in your body. You can contemplate the stars that died to create those elements. The universe, through you, is observing itself. This is not a metaphor. You're literally the universe arranged in a particular configuration that permits self-awareness. Consciousness is the cosmos becoming conscious of itself. The scale of the cosmos also invites humility, a recognition that human concerns, the conflicts and competitions and worries that dominate our daily lives, are vanishingly small when viewed from a cosmic perspective. Borders and nations and empires rise and fall, but the stars do not notice. Entire civilizations could flourish and collapse, build great cities and wage great wars, create art and science and philosophy, and the universe would continue unchanged, indifferent to our dramas. This does not make our lives meaningless, but it does suggest a certain perspective, a recognition that the things we often treat as desperately important are, in the grand scheme of cosmic time and space, transient and local. The astronomer Carl Sagan famously remarked on this perspective in his reflections on the pale blue dot photograph, an image of Earth taken by Voyager 1 from a distance of 4 billion miles. From that vantage point, Earth appears as a tiny speck, less than a pixel, suspended in a beam of sunlight. Sagan wrote, "Consider again that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. On a mote of dust suspended in a sunbeam." Sagan's point was not to diminish the value of human life, but to highlight the fragility and preciousness of our world, the only home we have ever known, a tiny oasis of life in an otherwise barren cosmos. The cosmic perspective, he argued, should inspire not despair but responsibility, a commitment to protect the conditions that make life possible, to cherish the biosphere that gave rise to us, to work toward a future where humanity survives and flourishes. At the same time, we should not confuse physical size with importance or value. A black hole is vastly larger than a human, but it does not think, does not create, does not love, does not compose symphonies or write poetry or build particle accelerators. Complexity and consciousness are rare in the universe as far as we know. Most of the cosmos is empty space or inert matter, hydrogen and helium gas drifting through the void, or dark matter whose nature we do not yet understand. The fact that humans are small does not diminish the fact that we are complex, that we build civilizations, create art, explore the universe, seek to understand our place within it, and experience the subjective richness of conscious existence. Value is not a function of size. The cosmic perspective can be liberating. It can free us from the tyranny of ego, the belief that we are the center of everything, the assumption that the universe revolves around our concerns. It can inspire wonder and awe, a sense of connection to something larger than ourselves, a recognition that we're part of an immense and ancient story. It can also foster a sense of responsibility. We are the universe's way of knowing itself, and that knowledge carries with it an obligation to preserve the conditions that make knowledge possible, to ensure that consciousness, having emerged after billions of years of cosmic evolution, does not extinguish itself through short-sightedness or carelessness. Ultimately, the question of whether the scale of the universe diminishes or enhances human significance depends on what we value, on how we define meaning. If meaning requires that we be the center of the cosmos, that the universe was created for us, that our existence is the primary purpose of all that is, then the scale of the cosmos is indeed diminishing. We are not the center, we are not the purpose. The universe is indifferent to us. But if meaning can be found in the act of understanding, in the experience of consciousness, in the relationships we form and the beauty we create, then the scale of the cosmos does not diminish us. It elevates us. We are the part of the universe that has learned to ask questions, to seek answers, to wonder at the immensity of it all. That is worth celebrating. The observable universe, vast as it is not the universe. It is merely the part we can see, the region from which light has had time to reach us since the Big Bang 13.8 billion years ago. Beyond our cosmic horizon lie realms forever hidden from view, regions of space that are receding from us faster than light can travel, galaxies and stars and perhaps civilizations that exist but are causally disconnected from us. No signal from them will ever reach Earth, and no signal from Earth will ever reach them. Because the expansion of space between us and them exceeds the speed of light. What lies beyond the observable universe? We do not know, and we may never know. The nature of cosmic horizons prevents us from observing beyond a certain distance, but we can speculate, guided by theory and indirect evidence. One possibility is that the universe is finite but unbounded, a concept that is difficult to visualize but mathematically well defined. Imagine the surface of a sphere, like the surface of Earth. It is finite in area. You can measure it, but it has no edge, no boundary. You can travel in any direction forever without reaching an end. If you keep going in a straight line, you eventually return to where you started. The universe might have a similar geometry in 3 dimensions. If it does, then traveling far enough in one direction would eventually bring you back to your starting point. Light from distant galaxies might loop around the universe multiple times, creating duplicate images of the same objects in different directions. Astronomers have searched for such duplicate images, looking for identical patterns of galaxies or identical features in the cosmic microwave background radiation that would indicate the light had circumnavigated the universe. So far, no convincing evidence has been found. However, observations of the cosmic microwave background suggest that the universe is flat, or very nearly so, in its geometry. A flat universe, in the language of general relativity, is one where the rules of Euclidean geometry apply on large scales, where parallel lines remain parallel forever, where the angles of a triangle sum to 180 degrees. A flat geometry implies that the universe is likely infinite in extent, stretching on forever in all directions without end. If the universe is infinite, then it contains an infinite number of galaxies, an infinite number of stars, an infinite number of planets, an infinite number of atoms. There is no edge, no center, no boundary. Every point in an infinite universe is equivalent to every other point. You're not at the center because there is no center, and yet from your perspective, you appear to be at the center of your observable universe, surrounded by a sphere of visibility that extends 46.5 billion light-years in every direction. Every other observer anywhere in the universe sees the same thing from their own location. This is the homogeneity and isotropy that the cosmological principle assumes. In an infinite universe, probability becomes strange and unsettling. Any event with a non-zero probability, no matter how unlikely, will occur not just once, but infinitely many times. If the universe is infinite and the distribution of matter is roughly uniform on large scales, then there are infinite copies of Earth, infinite versions of you, infinite variations on everything that has ever happened or could happen. Somewhere out there, beyond your cosmic horizon, there is another Earth, identical to this one in every detail, where another version of you is reading these exact words at this exact moment. And there are infinite variations. Earths where you made different choices, where history unfolded differently, where the laws of physics are the same but the initial conditions were slightly different. This idea is deeply counterintuitive and troubling to many people. It suggests that nothing is unique, that every possible outcome is realized somewhere, that free will, if it exists, merely determines which version of you in which branch of the infinite multiverse you find yourself. But it is a logical consequence of an infinite universe with finite possible configurations of matter. Given enough space and enough time, every possible arrangement will occur, and occur infinitely often. Another possibility is that our universe is part of a multiverse, a vast ensemble of universes, each with its own properties, its own laws of physics, its own history. Some versions of multiverse theory arise from cosmic inflation. The idea that the early universe underwent a brief period of exponential expansion, growing from subatomic scales to macroscopic scales in a tiny fraction of a second. Inflation was proposed to explain why the universe appears so uniform, why the cosmic microwave background has almost the same temperature in all directions, even though regions on opposite sides of the sky have never been in contact. But inflation, if it occurred, might not have ended everywhere at once. Different regions of space could have stopped inflating at different times, creating separate bubble universes, each expanding and evolving independently. These bubble universes might have different physical constants, different numbers of spatial dimensions, different particles and forces. The properties we observe in our universe, the strength of gravity, the charge of the electron, the speed of light, might be accidents of our particular bubble, not universal laws at all. We live in one bubble, but others exist, forever beyond our reach, separated from us by regions of space that are still inflating. String theory also predicts a multiverse, often called the landscape, a vast number of possible configurations of the extra dimensions, each corresponding to a different universe with different physical laws. The number of possible universes in the string landscape has been estimated at 10 to the power of 500, an incomprehensibly large number. Each universe in the landscape is a different solution to the equations of string theory, a different way of curling up the extra dimensions, yielding different particles, different forces, different constants. If this is true, then our universe is just one among an unimaginable multitude, and the laws of physics we observe are not the only possible laws, but merely the laws that happen to apply here. Some versions of multiverse theory propose that every quantum event spawns new universes, a many-worlds interpretation of quantum mechanics. Every time a particle's wave function collapses, every time a measurement is made, reality splits into multiple branches, one for each possible outcome. In this view, there are infinite versions of you living out every possible history, making every possible choice, experiencing every possible fate. The multiverse becomes a branching tree of universes, constantly multiplying, forever inaccessible to one another because each branch represents a different outcome of quantum events. These ideas are speculative. They extend beyond the reach of current observation and may forever remain untestable. We cannot observe other universes if they are causally disconnected from ours. We cannot measure the properties of regions beyond our cosmic horizon. But these ideas arise naturally from our best theories, from attempts to explain the features of the universe we do observe, and they force us to confront the possibility that the observable universe, vast as it is, represents only the tiniest fraction of all that exists. The true scale of reality might be incomparably larger than we have imagined, extending not just beyond our cosmic horizon, but into dimensions and configurations we cannot perceive or conceive. The ultimate question, the deepest question, is whether the universe or multiverse has an edge, whether existence itself has a boundary. Does reality extend infinitely, in all directions and through all dimensions, without limit? Or is there a point beyond which nothing exists, a boundary between being and non-being? This is not a question science can currently answer. It may be a question science can never answer, a question that lies forever beyond the reach of empirical investigation. We are bound by the speed of light, by the age of the universe, by the limits of observation and experiment. Some truths about reality may be forever beyond our reach, questions we can ask but never answer, mysteries we can ponder but never solve. The scale of the universe, from the Planck length to the observable cosmos and perhaps beyond, to an infinite or multiversal reality humbles us, but it also inspires us. It reminds us that we are part of something vast and ancient and mysterious, that the cosmos is far stranger and more wonderful than our ancestors ever imagined, and that there is always more to discover, always another layer of reality waiting to be revealed. We have travelled across the full scale of existence, from one end of reality to the other. We began at the edge of the observable universe, 93 billion light-years across, containing 2 trillion galaxies and more stars than there are grains of sand on all the beaches of Earth. We descended through superclusters and galaxy filaments, structures stretching billions of light-years, vast cosmic threads surrounding even vaster voids. We passed through the Milky Way, our home galaxy with its hundreds of billions of stars, and through the solar system, the small collection of planets orbiting a very ordinary star. We crossed Earth, the only world we know that harbours life, and descended through the human scale, through cells and molecules and atoms into the nucleus, through quarks and leptons and the theoretical vibrations of strings at the Planck length, 10 to the power of minus 35 meters, where space-time itself dissolves into quantum foam. The span is incomprehensible. From the Planck length to the observable universe is a journey across 62 orders of magnitude, a factor of a billion, 10 to the power of 62, a number so large that writing it out in full would require 62 zeros after the 1. No analogy can capture this gulf. No metaphor makes it intuitive. The universe is simply too large and too small for human minds to grasp directly. We can calculate it, represent it mathematically, visualize it in simplified models, but we cannot truly comprehend it in the way we comprehend a tree or a mountain or a city. And yet, here we are, creatures of modest size, living on a planet that is a speck in a galaxy that is a speck in a supercluster, that is a speck in the observable universe, which may itself be a speck in a larger cosmos we cannot see. We are made of atoms forged in the hearts of dying stars, assembled through billions of years of cosmic evolution, organized into structures complex enough to ponder our own existence. We are witnesses. We are the universe observing itself, asking questions about its own nature, seeking to understand its own scale and history and fate. The true scale of the universe is not just a matter of size or distance or number. It is a matter of perspective, of recognizing where we fit within this immensity, of understanding that we are both unimaginably small and astonishingly significant. Small because we occupy a tiny fraction of space and time, because the cosmos extends far beyond us in both directions, because we exist for a brief moment in a universe that will endure for trillions of years. Significant because we are the part of the universe that has learned to ask questions, to seek answers, to wonder at the scale of it all. We exist on borrowed time. The atoms in our bodies will one day disperse back into the cosmos. The sun will eventually exhaust its fuel and expand into a red giant engulfing Earth. The Milky Way will collide with Andromeda. Stars will burn out, galaxies will drift apart, the universe will continue expanding, accelerating, growing colder and emptier, until entropy claims everything, until the last stars fade and the last black holes evaporate and nothing remains but a thin soup of particles spreading ever farther into an infinite darkness. But we're here now. Consciousness has emerged. Meaning can be found not in the indifferent vastness of space, but in the connections we make, the knowledge we gather, the beauty we create, and the understanding we achieve. The universe is vast beyond imagining, and we are small within it, but we are not insignificant. We are the part of the universe that has learned to comprehend itself, to map its structure, to calculate its age, to trace its history from the Big Bang to the present, and project its future to the end of time. If this journey has changed how you see the cosmos, if you have gained a new appreciation for the sheer scale of existence, hit that like button and subscribe. There are more mysteries waiting, more scales to explore, more questions to ask about the nature of reality. The universe does not stop revealing itself to those who are willing to look, to those who are curious enough to peer into the darkness and wonder what lies beyond. Thank you for travelling with me from the Planck length to the edge of the observable universe and back again, from the smallest possible scale to the largest we can imagine. Until next time, keep looking up and keep looking inward. Keep asking questions, keep seeking answers. The truth is always larger than we think, stranger than we imagine, and more beautiful than we can fully comprehend.